Hello, and welcome to this online course on mapping signal processing algorithms to architectures. In this introductory video, I am going to go over some of the concepts that we are going to cover as part of this course. And we will start by looking at some definitions related to the title of the course, then go over some prerequisites, what you can expect to learn as part of this course, and some minor administrative details at the end. So, the main concepts that we are going to look at in this course, from the title you can see there are three major parts to it: mapping, signal processing algorithms, and architectures. So, what I am going to do now is to go over these components of the title one by one. So, let us start with a signal. What do we mean when we talk about a signal? A dictionary definition of signal says, one of the dictionary definitions incidentally, says it's a detectable physical quantity or impulse such as a voltage, current or a magnetic field strength by which messages or information can be transmitted. Now, an example of a signal intentionally which is not a voltage or a current or a magnetic field strength is something that I have shown on the side, on the right hand side. You are probably all familiar with it. It's a QR code. Why do I call it a signal? Because in this case the code by itself is not the signal, but the pattern of light and dark squares and the light that is reflected from it is essentially what constitutes the signal. So, the next question that comes up is, what kind of processing are we talking about? First of all, what's the dictionary definition of processing? One of the definitions says to subject to examination or analysis, and in this case that's precisely what we would like to do with the QR code, right? We would like to say, okay, I have a QR code, I first need to detect it, find out the exact boundaries of the code, see what sense I can make of how big it is, where are the left, right, top, bottom edges, and once I have done that, can I then extract some useful information from it? All of that essentially constitutes processing. So, in this case, for example, the first step that we would need to do in order to process this QR code would be to detect it, after which we would need to align it so that we can then start looking at the specific bits, and finally slicing. What I mean by slicing is detecting whether something is white or black and deciding whether it's a 1 or a 0. So, detection would essentially mean finding out the bounding box, the boundary of this QR code. You can see over here the three squares at the corners make the detection as well as the alignment job much easier. And after that comes the question of both the alignment, which means making sure that we have not rotated or sheared the image in any way, and then slicing, which basically says, okay, how do I take those black and white pixels and convert them to a string of ones and zeros. Okay. So, all of that broadly falls under what we mean when we are talking about processing a signal. So, the third part of that is an algorithm, and the dictionary definition of this is a step-by-step procedure for solving a problem or accomplishing some end. Now, in this case what we essentially have is, for the case of the QR code, an example algorithm would be something which essentially goes through some kind of correlation, matching all the values of the pixels that have been obtained and finding out where those square patterns are located in an image. Once those square patterns have been detected, the next step would be, can you correlate them and find out are they rotated by a certain angle. The next step after that would be, once you have got the angle correct for any misalignment, rotation and so on, all of those have a very well defined sequence of steps that are involved over there. So, as far as we are concerned, the definition of algorithm remains pretty much the same. We have some kind of processing that we want to implement on a signal, and the algorithm itself is the sequence of steps that we need to follow to do this. So, there are signal processing algorithms as such have many different properties that set them apart from the kind of algorithms that you might study in a computer science course. For example, we are not really going to be talking about things like sorting and searching or database type algorithms in this course. We are primarily concerned with signal processing, and one of the classic hallmarks of signal processing algorithms is that they are typically numerically intensive, which means that we need to be worried about how we represent numbers and the number of bits that are used in order to represent a given numerical value. Signal processing algorithms also typically have limited or even no control flow. So, to understand what exactly I mean by control flow, a very simple example in a programming language would be a if statement in a language like C. So, a sorting algorithm, for example, would definitely have some kind of a statement that says if A of I is less than A of j, then swap or don't swap, right. So, that if condition is essentially some kind of a control flow. Depending on whether the condition was satisfied or not, one or other branch would be taken. Signal processing algorithms typically have very limited such control flow branching. In other words, another term that we will come across increasingly as we go through the course is that they exhibit something called a data flow behavior. All the input data primarily goes through the same set of operations all the way until it is processed to the end. The related aspect is that you also have a behavior that is sometimes called streaming, which means that they are working with samples of data, right. And the samples could come from multiple sources. It could be an analog to digital converter, it could be file storage, it could be a camera, and the rate at which the samples are received are often determined by physical factors. What I mean by that is, for example, we know that the human ear is only sensitive to sounds up to around 20 kilohertz or so, which means that if you want to record audio such that it can then be accurately reproduced for a human being to listen to, then you only need to sample at somewhere around a little over 40 kilohertz at the most, right. That is a purely physical determination. It has nothing to do with your computational capabilities. It does not matter how fast your computers are, you still need to sample only at 40 kilohertz. So, let us look at some examples of what I am going to refer to as signal processing algorithms. One class of such algorithms are what are used for analysis. This would include filtering, where for example you want to extract data that falls in one particular range of frequencies. Finite impulse response and infinite impulse response filters are examples. Transforms, the discrete Fourier transform, discrete cosine transform, these are also types of signal processing algorithms that are used for analyzing a signal and determining whether it has, for example, frequency components in a certain range. Compression is another class of signal processing algorithms, typically applied, for example, in speech coding, image compression, vector quantization that is used in the context of speech compression, right. All of those have different kind of numerical algorithms that broadly can be classified, that all fall under the category of signal processing algorithms. And then you have comparison. Examples of this would be speech recognition. Given a sample of speech, can I in some sense compare it against other known samples and find out which one it matches most closely, and in that way recognize what it was that the person spoke. Similarly, image recognition, it has become very popular these days because of the success of certain new types of algorithms that are able to recognize images with a very high degree of accuracy. Now, a word about what I am going to call non-traditional signal processing algorithms. What I mean by non-traditional is that these do not typically exhibit all the characteristics of signal processing algorithms. In other words, what we typically have in mind is linear, time invariant, numerical computation, right. One example is cryptography, and where this sort of differs from the traditional signal processing is you are not talking about linear systems necessarily, and you are definitely not talking about numerical computations. It is mostly bit manipulation that is involved. Error correcting codes are another example. There is some amount of bit manipulation, but also a significant amount of number crunching, especially on the decoding side of error correcting codes. And nowadays, the flavor of the day, neural networks, they are nonlinear. In fact, the nonlinearity is one of the main strengths that gives them many of their useful features, but they are heavy on number crunching. So, if these do not satisfy all the regular requirements of signal processing algorithms, why am I including them here? Because most of the concepts that we are going to study in this course apply to these kind of systems as well. It does not matter whether they are nonlinear or whether they relate to bits instead of numbers, as long as they exhibit certain properties such as data flow behavior and similar kinds of things that allow us to do certain analysis, and can allow us to break down the computations that are being performed on them, the ideas discussed in this course will be of use in understanding and implementing such systems. Alright, that was quite a long time spent on the signal processing algorithms aspect. So let's look at the last part of the title. The word is architecture, and one dictionary definition is the formation or construction resulting from or as if from a conscious act, a very formal kind of definition. Probably a more useful one in our context is the manner in which the components of a computer or computer system are organized and integrated. Now, why do I say that this is more useful? Because this is pretty much what we are going to be looking at. How do we take different hardware components, put them together in a way that gives us useful structures that can be used in order to implement certain algorithms. So, the architecture itself will consist of the different hardware components, how they are connected together, and the rest of the course essentially relates to how do we analyze the algorithm and then figure out how to use that architecture efficiently. Now, architecture has a wide range of possibilities. At one end, which is what we would study if we were looking at it purely from the point of view of a VLSI designer, you would have something called fully custom designed hardware. Every adder, every multiplier, every register that is required for your design, you would decide it and decide exactly how big it should be and place them over there and connect them together. Obviously very difficult to do, but probably the best if you want to get the highest performance out of your system. Semi-custom hardware makes a few design trade-offs. This word trade-offs is again something that you would encounter repeatedly in any design course. Once again, in this course too, we will be considering trade-offs. We are trying to understand, if I sacrifice some multipliers, can I then replace them with adders? If I sacrifice something in area, will I be able to make up for it by running the entire system faster, right? All those kind of trade-offs are what we need to do. So in the semi-custom hardware, what we do is we use some kind of standardized modules. Rather than going for a full custom design, we use standardized modules like a pre-designed adder, a 32-bit multiplier. All of those are standard designs which we do not try to optimize further. We use them and then maybe see how we can connect them together in certain ways. Programmable hardware, especially these days using FPGAs, field programmable gate arrays, is a very popular and a very powerful option for the kind of things that we want to do. It gives a lot of flexibility in terms of what can be done, but in addition to that, it also gives you speeds and the ability to exploit parallelism that you can only do with hardware. Domain-specific programmable processors include the traditional digital signal processors and nowadays the GPUs, graphic processing units, or sometimes as they are called GPGPUs, the general purpose graphics processing units. Now, why do I say domain specific? Because these kind of processors have certain aspects where they have been tuned to perform particularly well on a class of problems. In our case, the domain would be signal processing and the class of problems would be ones that are heavy on numerical computation. At the other end of the spectrum from fully custom hardware is the general purpose programmable CPU. That would be the CPU that you have, that any one of you has in a computer that you are using. It is capable of performing any kind of computation. It is able to do a lot of computations well for the simple reason that people have spent such a lot of time working on it and optimizing it in order to achieve high speeds. But if you really look at a specific algorithm, let's say a filtering or a Fourier transform, it may not give you the best solution in terms of a combination of the speed, power, area, etc. that is required. And finally, we come to the first part of the title, mapping. There is no really relevant dictionary definition over here. What we mean when we talk about the word mapping is to basically say we are going to understand the constraints of the algorithm and the architecture, specify which elements of the algorithm will be implemented by which elements of the architecture. For example, I might have a number of additions, some comparisons, some multiplications. All of them could potentially be done by one single arithmetic and logic unit. But if I had additional hardware that is capable of doing only, let's say, addition, I could try and move some of my add operations onto that hardware. Similarly, if I had some other multiplier units, maybe I could use those for multiplications, right? How do I make efficient use of all the hardware that is available to me? That's basically what this is trying to answer. Once we have come up with a possible solution, the next thing that we need to do is measure the effectiveness and usefulness of that mapping. How good is it? Is it really making efficient use of all the hardware that's available to you, or is it excessively relying on one particular unit and wasting all the others? And finally comes the stage of, okay, we have measured the effectiveness, can we modify either the algorithm or the architecture that's available to us with the aim of improving some of the metrics that we tried to measure in step 3. And of course, this is an iterative process. Go back to step 1 and repeat the entire thing once again, right? Now you have got a modified algorithm and a modified architecture. Once again, understand them. What are the constraints? How do you map the elements of the algorithm onto the architecture? Can you measure its effectiveness and can you improve it further? So the approach that I will be focusing on as far as this course is concerned is, of course, initially we will look at most of the background theory, right? What are certain useful properties of DSP algorithms? What are the kinds of things we need to do in order to understand what can be made use of in order to come up with better implementations? And also what are limitations on how fast or how efficiently they can be implemented on any given kind of architecture. But for the most part, the core idea that I am following over here is that rather than custom designing everything from scratch, we will be looking at the signal processing algorithm and trying to see, can we come up with specific hardware accelerators, that is custom modules that perform specific functions. In other words, we will be starting with systems that are purely written in software, that try to do almost the entire algorithm, the entire processing in software. But then because they are not able to perform well enough, meaning that either they are not fast enough or they consume too much power or they require too many resources, we then see if we can identify the bottlenecks, the specific parts of that program that could benefit from being moved into custom hardware, and then see if we can generate custom hardware that would allow us to implement those specific portions of the overall system. Now what this means is we will have a general purpose CPU, a processor that is capable of running the entire algorithm, and we will also have some kind of custom peripherals whose job it is to handle some specific parts of the computation, which means that the question of how does that CPU talk to those peripherals, how do we create buses that allow us to communicate between multiple different kinds of peripherals, what are the limitations on memory interfaces, what are the bottlenecks that we come up with, all those are also design factors that we will consider as we move forward in the course. So can we briefly look at what you as a student could hope to learn by the end of this course? In terms of pure learning objectives, one of the things that I would hope should be clear to all of you by the end of this would be that you should be able to describe characteristics of computationally intensive algorithms. What that means is you should be able to identify which are the bottlenecks or critical computations that are present in any kind of a computationally intensive algorithm, right? As we will see later, computation is not the only bottleneck. Communication, in other words, how do I read and write data from memory, is just as important a problem. Both of these are things that you should be able to look at an algorithm and a given architecture and identify what the problems are likely to be. Given an algorithm and given an architecture, you should be able to map the algorithm onto the architecture and measure certain metrics of quality, right? So that will essentially be the kinds of scheduling algorithms that we will look at further down in this course. In addition to that, you should be able to look at the algorithm, and once you have the metrics of quality, identify possible modifications to the algorithm that might improve the quality of the solution, right? What I mean by solution is improve the metrics that we were measuring. Is it the area, the speed, the power, or any other combination of those metrics that we are looking at? Similarly, can we identify modifications to the architecture that would allow us to implement this particular algorithm in a more efficient way? Now, as part of this course, I will be giving a number of demonstrations which basically look at certain simple signal processing algorithms and going through the process of how do we actually create a test setup, write the code, implement it, test that it's working correctly, use high-level synthesis tools to implement hardware accelerators that can then run on an FPGA platform. Now, why am I specifically mentioning that these are going to be for demonstration? Because given the online nature of this course, it is difficult to have to make sure that everyone can have the same kind of facilities that will allow you to actually implement all of this and submit them as assignments. On the other hand, I will be discussing them in sufficient detail that anybody who is interested can get hold of the tools and try them out on their own as well. But they will not be part of your final grade. I do hope that most of you will take this part seriously and will hopefully benefit from it in terms of actually putting things on hardware and seeing the benefits of the approaches that we are looking at in the course. Some prerequisites, the basic concepts of digital signal processing, of course, you are expected to know, right? So, at the very least, you need to understand what I mean when I am talking about a filter or a transform. Some basic knowledge of compression recognition algorithms such as image recognition are helpful but not essential. We will not be developing new algorithms or looking into those in much detail. The fundamentals of hardware design, what I mean by that is the basics of digital design, timing, critical path analysis, maximum operating frequency, power dissipation, capacitance, effects of technology scaling. All of these you need to have some idea of what they are. I will be going over a very brief overview of both of these in the next video, but the basic concepts of digital design you should know, otherwise you will probably find it hard to fully appreciate what I am talking about over there. Now, as far as programming is concerned, as I told you, we won't have programming assignments in this course. On the other hand, the demo portions will definitely be using C or some minimal portions of C++ and to some extent Verilog. And the reason for these is because the code will be written over there and I will be demonstrating how you can actually go through the synthesis process and also looking at the Verilog code and trying to understand what has been generated. In order to properly appreciate these portions, you need to have some basic understanding of C or C++ and Verilog. Now, once again, this is beyond the scope of what can be covered in this course, so hopefully you would be able to obtain this information from other sources. Reference material, there are some useful books. In fact, the first book that I mentioned here, VLSI Digital Signal Processing by Keshav Parhi, and the second book, DSP Integrated Circuits by Lars von Hammer, both are nearly 20 years old at this point. Now, as far as I am concerned, I think that's perfectly alright for a reference book because the material here is not very new. The core ideas of mapping signal processing algorithms to architectures have been well studied for probably 30 or 40 years, right? So, a lot of the material that is present in these, for example, some of the theory, the properties such as the iteration period bound, all of those are discussed in a fair amount of detail in these books. Having said that, I would not really call them textbooks because I will not be following them very closely. They are useful reference material. There will also be use of quite a bit of other outside reading material which I will post pointers to on the course website as we move forward. And lastly, a couple of administrative details. The website for this course, hopefully all of you are already familiar with it. I have put it up over there in case you need it for reference. My name is Nitin Chandrachudan. I can be reached by email nitin@ee.iitm.ac.in, but I would sincerely request you to use the forum for the course as far as possible because it allows other people also to respond, including certain teaching assistants who will be available on the course and who will be able to respond to you as and when, and probably faster than I can, because otherwise it might become, I don't want to become the bottleneck as far as responding to questions is concerned over here. As far as interaction with the class is concerned, the forum, as I mentioned earlier, will be used for all announcements and also is open for discussion. There are two fora, in other words, as far as this course is concerned. One will be used only for announcements. The other is for open discussions. You are free to post questions over there. I will try my best to respond to as many of them as I can. There are teaching assistants too who will also be able to help. We will also have a few online meeting sessions, meaning that it will be a specific time when I will be available and can be contacted as part of this course. The exact times of those will be announced later on the website. So that pretty much sums up this introductory video. As I said, I will be moving forward with a review of digital systems and number representations and so on, the basic background that hopefully you are already familiar with. So the remaining lectures in week 1 may be already familiar to some of you, but if not, then please make use of those in order to brush up on background that you might be missing to some extent. And I hope you are able to benefit from this course, and all the best.